Hi, I'm Mr. Parker and this is question 6 on the OCR Mechanics 1 paper from June 2010. For more questions on this exam paper, click the link here or check in the video description. In question 6, a block B of mass 0.85 kilograms lies on a smooth slope inclined at 30 degrees to the horizontal. B is attached to one end of a light and extensible string which is parallel to the slope. At the top of the slope, the string passes over a smooth pulley. The other end of the string hangs vertically and is attached to a particle P of mass 0.55 kilograms. The string is taut at the instant when P is projected vertically downwards. In part 1, we need to calculate the acceleration of B and the tension in the string, and then the magnitude of the force exerted by the string on the pulley. Let's start by drawing a diagram of the problem. So we've got a block on the slope, and it's attached by a string to a particle P, which is hanging vertically here. Adding forces to the diagram, we've got a weight force which is vertically downwards from the centre of the block of 0.85 G, and we've got a tension pulling the block up the slope which we'll call T. There is also a normal contact force coming out from the block, but since the slope is smooth we can ignore that for this problem. On particle P, we've got a weight of 0.55 G pulling downwards and a tension pulling upwards of T. Notice that with a smooth pulley, the tension in the string this side of the pulley is the same as the tension this side of the pulley. The question also says that the string is taut at the instant when P is projected vertically downwards. That implies that it's going to accelerate downwards, so I'm going to put an acceleration over here, vertically downwards, and an acceleration up the slope for the block here. If it turns out that that's not the case and that it's sliding down the slope, then all that will happen is that our value for A would end up being negative, so it doesn't matter if we set this acceleration up in the wrong direction. So in part A, we're trying to calculate values for acceleration and tension. To do that, we're going to form two simultaneous equations. I'm going to start by thinking about particle P. And if I resolve the forces acting vertically on P, we'll take downwards as positive, we get 0.55 G minus T equals mass times acceleration, so that's 0.55 multiplied by A. Notice that we've chosen the positive direction, downwards, to be the same direction as the acceleration. That's usually a good thing to do and it makes the calculations easier. Rearranging this, if we added T to both sides and subtracted 0.55A, we end up with T equals 0.55 G minus 0.55A. We'll call that equation 1. Next we'll consider the forces acting on the block in the direction of the slope. We'll take up the slope to be positive because that's the direction we've assumed acceleration is in, and we get a force T, and we're going to subtract a component of the weight force going down the slope. And because we're taking it in the direction that doesn't include the angle here, remember this angle the other side would be 30 degrees, then we can say that that force is 0.85 G sine 30. On the right hand side we have mass times acceleration, so that becomes 0.85A. Adding 0.85 G sine 30 to both sides gives us T equals 0.85A plus 0.85 G sine 30. We'll call that equation 2. Now that we've got two equations and they're both in the form T equals, we can set the right hand sides of these equations equal to each other. From here we'll collect terms together. We'll add 0.55A to both sides, that'll give us 1.4A on the right hand side, and we'll subtract 0.85 G sine 30 from both sides to give us 0.55 G minus 0.85 G sine 30. From here we can divide through by 1.4 and get a value using our calculator for A. And that gives us 0.875. Now that we've got a value for A, it should be fairly straightforward to find a value for T. I'm going to use equation 1. I get T equals 0.55 G subtract 0.55 times A, which we now know is 0.875. Substituting this into our calculator, gives us 4.91 if we round to 3 significant figures. As I've read ahead to part B, I know that the next part of the question requires this value for T, so I'm going to store this in my calculator as a value. To do that, I press the Shift button and then the store button here, and then I choose any of these red letters. I'm going to save it as A. That means now anytime that I press the alpha button and then A on my calculator, I'll be using that value. In part B, I'm looking to find the magnitude of the force exerted by the string on the pulley. This time, instead of looking at forces on the block and particle P, I'm going to think about what's happening to the pulley. As there's a tension in this string, from the perspective of the block, that tension was pulling upwards, but from the perspective of the pulley, that tension will be pulling away from the pulley, and it will also be pulling down from the pulley this side. So the way you have the forces depends on which object you are doing the calculations from the perspective of. As the pulley is not accelerating, we won't have any acceleration in this part of the problem. I'm now going to draw this as a force diagram. So I've labelled the forces A and B, and as we calculated the tension in the last question as 4.90, I've added that force on as well. So we've got a force going vertically down and a force going at 60 degrees here. I got this 60 degrees from the right angle triangle here where this angle was 30 degrees. In order to find the magnitude of the force on the pulley, I'm going to resolve in the vertical direction and the horizontal direction and then combine them forces to get a resultant force. So my forces are A and B, and I'm going to work to the left and also in the vertically down direction. So the component of force A that's going to the left is 0 because this force is completely downwards. That means the component of A going downwards is this 4.90 Newton force. For B, the component of B going to the left is going to be 4.9 multiplied by sine 60 because I'm not including the angle in the direction that I'm going. The component of B going vertically downwards is going to be 4.9 cos 60. Now I can find the components of the resultant force from A and B by adding the components of these forces in each direction. So to the left I've got 4.9 sine 60. But remember, this isn't exactly 4.9. I've got the value stored in my calculator, so I'm going to use that to be more accurate. So I've got A sine 60. That gives me 4.25 and so on. Because I'm going to use this value later, I need to store this as well. So I'm going to store this as B. For the vertical component, I'm going to get 4.9 add 4.9 cos 60. Remember, this is still stored as A, so I can do A plus A cos 60. And that gives me 7.36 and so on. As I'll need this value later as well, I'll store this as C. So remember, I've got B stored here and C stored here. In your exam, you might want to annotate which letters you've stored which values on your calculator to help you out. Now that I've got these two components, I can redraw this diagram as a right angle triangle involving a horizontal and a vertical component. So downwards I've got 7.36 newtons, to the left I've got 4.25 newtons, and my resultant force goes in between the two. So to calculate R, I get R squared is 4.25 squared plus 7.36 squared. On my calculator, all I need to do is B squared plus C squared because I already have these values stored. That gives me R squared. To get R, all I need to do is square root my answer, and I get 8.50 to 3 significant figures. In part 2, we've got some extra information. It says the initial speed of P is 1.3 meters per second, and after moving 1.5 meters, P reaches the ground where it remains at rest. B continues to move up the slope and does not reach the pulley. We need to calculate the total distance B moves up the slope before coming instantaneously to rest. So back to our original force diagram, this is what we've got before the particle P hits the ground. So we're going to do some calculations before it hits the ground, and then we're going to re-evaluate the situation once P has hit the ground. So in the extra information, it told us that P travels 1.5 meters down. That means that the block will travel 1.5 meters up the slope. Its initial velocity was given as 1.3 meters per second. The final velocity is something we don't know yet, but it's going to be something we need to work out. The acceleration we worked out in an earlier part of the question was 0.875, and we don't know how much time this movement takes. So for the movement before P hits the ground, we know how far it actually travels, 1.5 meters. We don't need to calculate that, but what we do need to figure out is V. And the reason for that is, if we want to do some calculations for the block after P has hit the ground, we need to know what speed the block is travelling at the instant when P hits the ground. So to do that, I'm going to use my Suvat equations. The one I want is v squared equals u squared plus 2as. So substituting in my values, I get v squared equals 1.3 squared plus 2 lots of 1.5 times 0.875. And that gives us v squared is 4.315. So to get v, we just need to square root our answer, and we get 2.077 and so on. As we're going to use this value later, we'll store it in our calculator as d. Next, we're going to consider the situation after P has hit the ground. So if we look at this diagram here, the reason that there is a tension in the string is because particle P is moving towards the ground and is pulling on the string. After this particle has hit the ground, there will no longer be any tension in the string, it will go slack. And that means the tension forces will disappear, and the situation we're left with is the block with just a weight force acting downwards on it. So if we now resolve forces on the block down the slope, we get a component of this weight force, which is 0.85 g sine 30, and that's going to equal mass times acceleration 0.85 a. As we've got a 0.85 on both sides of the calculation, we can cancel to get a equals g sine 30. Sine 30 is just a half, so we get left with a equals 4.9 meters per second squared. For the next part we have to be careful though, because the acceleration we've just calculated is down the slope, but the velocity we have just found here was up the slope. That means we need to be careful which direction we consider is positive in the next part of the problem, and I'm going to consider going up the slope as still positive because that will be consistent with the first part up here. So when we put this value of a into our Suvat equations, we're going to put it in as minus 4.9 meters per second squared. So we're looking to find the distance it's travelled after P has hit the ground, so we don't know that yet. Our value for u will be equal to our value for v from the last part of the question. We're looking to find how far it's travelled when it's at instantaneous rest at the top of the slope. That makes v 0, and we're not interested in the time. So now we'll form an equation of motion after P hits the ground, and we're going to use the same equation again because we've got u, v and a, and we're looking to find s. So we get 0 squared equals 2.077 squared. As a is negative, we're going to get minus 2 times 4.9 times s. If we rearrange by adding the second term to both sides of the equation, we get 9.8s. I've worked out the 2 times 4.9 here, equals 2.077 squared, and if we divide through by the 9.8, we'll get a value for our distance. So remember, I've got my value stored as d. I'm going to square it and then divide by 9.8. And that gives me 0.44 and so on meters. Finally, I need to figure out the total distances travelled. Well, remember, it travelled 1.5 meters up the slope before P hit the ground, and then after P hit the ground, it travelled 0.44 meters up the ground. So all I've got to do is start with 1.5 and add on my new part, and that gives me 1.94 meters to 3 significant figures.